Hey guys, welcome once more to the KC YouTube space. Today we're going to be looking at the KC October exams 2022. But before we dive in, I have a couple of guys here. To my right, I have Beltus, who is the Chief Project Officer at KC. Beltus, we'll just throw one or two things to you guys, all right?
Hey guys, so as the Chief Project Officer at KC, I manage all ongoing projects, one of which is the upcoming STEM competition. I mean, last year we organized the first session of this. This year is level two, and this year there will be many more amazing rewards. I mean, in terms of cash prizes, obviously. And then the questions this year are going to be wild, out of this world. So, all you science lovers out there, here is your chance. Come and make your name.
All right, guys, thank you so much, Chief Project Officer. To my left is one of our amazing students of last year, Blessing. Yeah, Blessing, let's throw in something to these guys watching.
Hello, I'm Blessing. I was a Casey student and I'm proud to say Casey taught me a lot. Like I learned so much. And I know it's not like a global platform. So for those who are really far out there, the YouTube channel is also one place where you can learn a lot from. And feel free to leave your questions in the comment section. They'll reach out to you, we answer, and that's it.
Perfect. All right, guys, so let's dive right in. Okay, guys, so just before we dive in, we hope you consider, of course, liking the video, subscribing, and then turning on that notification bell so that you don't miss any other uploads from our channel. All right, now we can dive in. The diagram below shows 12-volt power supply with a negligible internal resistance connected to a uniform metal wire AB. The wire has length 1 meter and resistance 10 ohm. Two resistors of resistance 4 ohm and 2 ohm are connected in series across the wire. Alright, the currents I1, I2, and I3 in the circuit are as shown in the circuit above. Calculate I1, calculate the ratio. Alright, I'm just going to come over here and do the working here. So the Roman one says that we should calculate I1, but if you look at the circuit, you'll notice that our I1, of course, is a combination of I3 and I2 according to Kirchhoff's current law. So you come here, I1, this is I1 entering this particular node, is split into I2 and I3. So if I can calculate I2 and then I3, I sum those two currents, it gives me I1. Alright, so we're just going to come over here again, just write that out. I1 is I2 plus I3, and then to get I2, I need you to notice that we can simply get the voltage that is dropped across this wire here, because I2 is the current that flows through AB. Get the voltage that's dropped across AB divided by the resistance of AB. They've already given us the resistance of AB here to be 10 ohms. Voltage that is dropped across this wire is basically 12 volts, so you have 12 over 10 there, gives you the current I2. And then come over here, the total resistance here is 4 plus 2, which is 6. So the voltage that is dropped across this arm, remember that this arm like that is in parallel with this arm, so arms that are in parallel to each other have the same voltage that is dropped across them. So you actually have these 12 volts being dropped across this guy, so you have 12.6, that gives you I3. So our I1 is basically 1.2 plus 2, which gives us 3.6 amperes. We can go over, it says calculate the ratio X, where X is power in metal wire divided by power in series resistors. So power in this wire divided by power in this resistors. But the electrical power is basically the current that flows through this wire multiplied by the voltage that's dropped here. So we are going to get that to be I2, because I2 flows through this wire multiplied by this voltage. Again, remember that the same voltage drop here as it is across these two resistors. So we're going to get the current that flows in these two resistors, which is I3, multiplied by the voltage that's dropped across the two resistors, which is again V. So we're going to cancel that out. Basically, we're going to be getting I2 over I3, which is, remember that our I2 is 1.2 divided by 2, which gives us 6 over 10. So that's our ratio. Next part says that calculate the potential difference between C and D. Now, potential difference between C and D, we have to be very meticulous here. So we are going to treat C and D as some sort of differential nodes. We're going to come here and get the potential at C to just basically be VC. And then we're going to traverse from C all the way to D. Now from C to A, there's a potential difference there, which is basically VCA. Remember that CA is 40 centimeters long. So 40 centimeters means that this length is actually associated with a certain resistance, which we can calculate. And that resistance is basically, if this entire length is 100 centimeters, it means that this 40 centimeters is basically 40% the resistance of the entire wire, which is basically 0.4 multiplied by 10, right? So that's the resistance of this portion multiplied by this I2 gives you the potential that is dropped here. Then we can keep traversing and come to this particular portion. Remember that now this I3 is flowing in the same direction as our traverse, and this I3 that flows through this 4 ohm resistor, it means that the potential is dropped across this 4 ohm resistor will be a negative potential. All right, then all of that will be equal to the potential at D. So okay, let's just go down and write that equation now. So we're going to have VC at this particular point plus VCA. Why is it positive here? Because we are traversing the opposite direction to the current that flows through CA. Do you see that? So we are traversing like this, current is rather entering. So we have positive potential here. And then we go all the way to the potential drop across the 4 ohm. It's now going to be negative because traversing against this guy, right? So equal to V at D. So we actually make VC minus VD the subject. So this is VC here, bring VD this way, carry the other ones that the other way. So we basically have VC minus VD. That only gives us the potential between C and D. Can you see that? So we actually have V across the 4 ohm resistor minus VCA. Now V across the 4 ohm resistor, we can still use the potential divider rule, or just basically take this 4 multiplied by I3 that flows through this guy. And remember that our I3 is 2 amperes. So you can just take this 4 times 2, it gives you 8. It means that this potential is basically 8 volts. But you could still use the potential divider rule. So 4 divided by 4 plus 2 multiplied by the potential that is dropped across the two resistors in series. Right, that's what I've used here. So it gives you the potential across this one resistor minus the potential across CA, which is basically 0.4 multiplied by the resistance here, which is 10. Sorry, so we are going to get 0.4 here multiplied by 12, because remember that again, this is the complete voltage that is dropped across this wire, which is 12 volts, and again this length is just proportional to that. So we actually have this 0.4, and then we multiply with the total voltage that's dropped across the entire wire, which is good. So you now have the voltage that's dropped across this 40 centimeter portion. And then we actually have VCD now. Remember that VCD is of course the potential between C and D. It gives us 8 minus 4.8, which is 3.2 volts. So that's that for question 1, and then we can have the mark distribution like that for the exam. That's how the marks were distributed. All right, so let's go to the next question. So this is the next question. You can just pause the video right here and then read the question and then try to solve it on your own before checking how I've done it in the next slide. Okay, so we have a catapult can fire a pellet to a vertical height of 10 meters on Earth. It is taken to the moon, which has a radius of that 0.27 of that of the Earth, and which is composed of material of mean density 0.61 of that of the Earth. Calculate the acceleration due to gravity on the moon. Alright, so to calculate the acceleration due to gravity, we're just going to get the ratio of G on moon to G on Earth to be rho. That's density of the moon multiplied by the radius of the moon divided by density of Earth multiplied by the radius of the Earth. So this is a relationship that you can actually derive. So we can go on and then say that, all right, so but density of moon to that of the Earth, remember that it's just 0.61, okay? Because remember that the mean density, material of mean density 0.61 that of the Earth. So it means that density of moon to that of the Earth is basically 0.61, and then the radius of the moon to that of the Earth is basically 0.27. So basically have G, that's field intensity at the surface of the moon to that of the surface of the Earth. It's basically the product of 0.6 and 0.27. All right, so we actually have our result to be 1.6 meters per second squared. So the next part of the question says that the height to which the pellet could be fired on the moon. So the height to which a pellet could be fired on the moon. So how am I going to do that? We're going to assume that the pellet, of course, has the same initial kinetic energy on both heavenly bodies. So that's on the Earth, it has the same initial kinetic energy as it has on the moon. So that entire kinetic energy on the surface of the Earth is converted to potential energy at its maximum height. So again, on the surface of the moon, the entirety of the initial kinetic energy is converted to the potential energy at its maximum height. So we can use this conversion and then cancel out the masses, and then of course make height on the moon the subject formula, and then of course get the height on the moon as 62 meters, of course in two significant figures. So we can go over here, and then the next part says at what velocity would Owen Bradley, an astronaut on a human colonization mission of the moon, have to fire a rock from the moon such that it is freed from the moon's gravitational well. Okay, of course that's just finding escape velocity, and escape velocity is just basically the square root of t 2g surface of the moon multiplied by the radius of the moon. So we have field intensity at the surface of the moon to be 1.6. Radius of the moon, remember that is 0.27 radius of the Earth. But we know radius of the Earth, which is 6.38 times 10 to the power 6 meters. So we actually have that out, and then we have that V escape to basically be 2.3 times 10 to the power 3 meters per second. So again, you can have the mark allocations like that, and that's how they were distributed in our exams. The diagram below shows a ship fitted with a sail attached to a cable. The force on the wind on the sail assists the driving force of the ship's propellers. The cable exerts a steady force of 2.8 kN on the ship at an angle of 35 degrees above a horizontal line. By using vector analysis only, calculate the horizontal and vertical components of this force. Alright, so of course this is the tensional force in this cable, so we can actually just draw a vector diagram like this. It's tensional force at an angle, and then we have the horizontal components and then the vertical components, of course. So we actually have these components, and again this angle. So if this is 55 here, remember that this is the angle that this force makes with the vertical. So we have a vertical here. If this is 35, then of course the vertical will make an angle with this rope of 55, so that when you add up that 55 to 35 gives you 90 degrees. So again, come over here, this will be 35 degrees. So we can actually use sine rule here, because again, remember that we're using vector analysis, so we can use sine rule here. This force divided by sine of the opposite angle equals this force divided by sine of this opposite angle, which actually gives us Tx to be T sine 55. And our Tx, remember that our T is a tensional force here, which is 2.8 kilonewtons, which is 2.8 times 10 to the power 3 multiplied by sine 55. So our Tx is 2.3 times 10 to the power 3. And then to get Ty, we'll basically do the same thing, T over sine 90, right? Equals Ty over sine 35, which gives us Ty to be T sine 35, which gives us 1.6 times 10 to the power 3 newtons. And then the next part of the question says that the ship is moving at a constant speed of this, and the horizontal component of the force on the cable of the force of the cable on the ship acts in the direction in which the ship is moving. So this horizontal force acts in that direction the ship is moving. So the power, they're asking us to calculate the power the wind provides to the ship, setting an appropriate unit. All right, so the power is basically the force multiplied by the velocity. So force in that direction of the velocity will basically be our Tx multiplied by the velocity, and then we actually have the power to be Tx is 2.3 times 10 to the power 3, remember that? So multiply that with the velocity, gives us 1.9 times 10 to the power 4 watts. So we're going to go and solve the other part of the question the other way, this other part. So but again, this is how the max allocation were distributed. Okay, let's go to the other part. The cable has a diameter of this. Ayok Sandrine, a young physics experimentalist, carried out. It's just important I note that Ayok Sandrine is actually one of our amazing students we have at the center there. Very passionate, very curious, very enthusiastic about learning. What an amazing girl we have at the center there. Shout out to her. All right, so a young physics experimentalist. I hope that comes to pass, that she becomes a physics experimentalist in the future and probably gets to the very top pinnacle of that career. Carried out experiments on how the extension varies for various lengths of the wire. She plotted a graph of extension against length for different loads applied on the wire. Notice the slope of the graph is 0.15 in appropriate units. Calculate the modulus of elasticity of the cable when it exerts a force of 2.8 kilonewtons, stating how this value relates to the material's Young's modulus. Alright, so we're just going to get our data down there. Diameter is that, E over L, remember that is a slope. Then our force is basically 2.8 kilonewtons. So Young's modulus is basically stress on strain. So stress is force per unit area, strain is extension per unit length. So we can actually find modulus of elasticity, because modulus of elasticity is basically a term used in engineering for the product of a material's Young's modulus and its cross-sectional area. So what we are going to do is that we're just going to take this cross-sectional area here. So we have EA to be F L0 over E. So again, this EA here gives us our modulus of elasticity, which is basically lambda, and then our F, remember that is 2.8 times 10 to the power 3, and then remember that L0 over E is basically the reciprocal of this slope, because the slope is E over L. You're plotting a graph of extension against length, so L over E, where that gives you the reciprocal of this slope, which gives us 20 over 3. So multiply that out, we have modulus of elasticity of the material to be 1.9 times 10 to the power 4. But how do we relate this modulus velocity to the material's Young's modulus? Again, remember that Young's modulus is basically modulus velocity divided by the cross-sectional area of the material. So we can go ahead and say, all right, so cross-sectional area, if we find this cross-sectional area is basically 6.5 times 10 to the power 5 multiplied by the material's modulus of elasticity. So that's the relationship, and the mark allocation here is like that. Again, this was question 4. You can just pause the video and then just go through the problem, attempt solving it, and then if you have any difficulties, then you play the video and check out how I've solved it. All right. Okay, so the first part says electrons are accelerated from rest through a potential difference of these in an x-ray to calculate the resultant energy of the electrons in electron volts. So how do we get energy? Energy is basically EV. So in electron volts, it means I will just keep this E here and then multiply by this 10,000. So it's basically 10,000 electron volts. Perfect. So the next part of the question says that the wavelength of the associated electron waves. All right. So we're going to use the Broglie relationship here. So the um oh god, the momentum of the electron waves is basically equals to the Planck's constant divided by the wavelength, right? Oh man, this is wave particle duality of, or perhaps the dual nature of matter itself. So we can actually say streams of fast moving electrons like this can actually have wavelength by momentum by virtue of having a mass and a velocity, and then of course we can get to calculate an associated wavelength. So again, wavelength signifies the wave property, and then momentum signifies the particle property, again, hence the wave particle duality of matter. All right, so we can actually go on and say that, all right, so this lambda here is basically h over 2mev. So this has a derivation. I just hope that subsequently we're going to put up how this formula is derived. But again, it's just important that you know this for advanced levels. It's a very, very important question formula, especially paper 1 and a lot of paper 2 questions on quantum physics. All right, so we're just going to go ahead and put our Planck's constant, which is 6.63 times 10 to the negative 34, and then we get in this 2 multiplied by the mass of an electron, which is 9.1 times 10 to the negative 31 kilograms, and then the charge on an electron, and then of course the voltage, which is 10 to the power 4 volts. So we actually have associated wavelength to be 1.2 exponent negative 11. So we're going to come over here, and then the maximum energy and maximum wavelength of the X radiation generated. So maximum energy is basically EV. So that's our Emax. So EV is basically again, V is 10 to the power 4, and then E is 1.6 times 10 to the power negative 19. That's the charge on an electron. So we can actually have the Emax to be 1.6 times 10 to the negative 15 joules. So to get the wavelength, remember that if the energy is maximum, then of course the wavelength is going to be minimum, because again, energy and wavelength are inversely related. So if energy is maximum, this guy is minimum, and if this guy is maximum, energy is minimum. All right, so we are going to calculate the associated wavelength here by simply making the wavelength here the subject. So we are going to have hc over E, and our h is again is this, our c is speed of light, and then our E is basically the energy, which we have calculated above, and that gives us 1.2 times 10 to the negative 11. So we can actually have our mark distribution like that, and that's how we distribute it. On to the next problem. Okay, living wood contains radioactive carbon-14, which is in equilibrium with carbon in the atmosphere. 1 kilogram of carbon from living wood gives an average number of disintegrations of 255 per second. Take note that this is 1 kilogram of wood, all right? So that's 1 kilogram of carbon from living wood, sorry. So again, this is basically the activity per kilogram, okay? So we are getting activity per kilogram. Take note of that. Now, a sample of 20 millikilograms, okay, so that's like 2.0 times 10 to the negative 2 of carbon from wood of an Asian board gives an average number of disintegrations of 270 per minute. Now remember that this is not activity per kilogram, so you have to make sure that you find the activity per kilogram here. All right, so the half-life of carbon-14 is this. Calculate the age of the board. Yes, state and any assumptions made in your calculations. All right, so we are going to have 1 kilogram of living wood to be this, and then so this is the activity of 1 kilogram. So of all wood, The activity, remember that they gave you the activity per minute instead, 270 per minute, so you have to convert that to per second, like this guy over here. So that gives you about 4.5 per second. So remember that that activity is associated with 2 times 10 to the negative 2 kilograms. So once we get the activity per kilogram of old wood, that will give us 225 per second. That's basically just dividing all through by 2 times 10 to the negative 2. All right, so it gives you the activity per kilogram. So now our original activity divided by our final activity, that's activity of fresh wood divided by activity of old wood, basically gives us 2 to the power n. This is a very important relationship in reductivity. So activity of fresh wood divided by activity of old wood, it gives us 2 to the power n, and our n basically take lean on both sides, is actually going to be 0.1806. all right, that's of course in 4 dB. So we actually now have our t now to be, of course, nt half. So these two equations like this are always used in tandem, and they are very, very crucial for radioactivity. So t equals to nt half, and then we can actually say that, all right, so our n is this, our t half is this. So our the age of the wood, right, because this capital T is like basically the total time taken for that particular radioactivity, for that particular radioactive decay, or for the activity to drop from this activity to this activity. All right, so that's what T represents. So that gives us about 1005.8 years, which of course, respecting number of significant figures in physics, is about 1000 years. So our mark allocation here is basically 3 marks for this question, and that's it. All right, so question 5 says a charged oil drop of mass that falls vertically in air with velocity between two long vertical plates 5 millimeters apart. When a PD of that is applied between the plates, the drop now falls with a steady velocity at an angle of 58 degrees to the vertical. All right, state why the oil falls with a steady vertical velocity. All right, so this is our diagram here. When you now apply the electric field, so it falls at an angle. So this angle here is 58 degrees to the vertical, and then of course this electric field. So this is an electric field, it's following an electric field. So the electric force is actually equal in this direction, right? The electric field strength multiplied by the charge on the oil drop, and then the weight of course the oil drop is basically mg. So we can go ahead and say, explain why it falls with a steady velocity. Of course, because air viscosity here is balancing out the weight. So if air viscosity balances out this active force, then it falls with a steady velocity. So again, Roman 2 says calculate the charge Q on the oil. So to calculate this charge Q, we basically can say that, all right, tan theta, which is this angle here, tan is, remember, opposite, and opposite is eq here. We can actually write it down here as eq, opposite over adjacent, so we have eq over mg. So make sure the subject is basically mg tan theta over e. So again, our E, remember that E is electric field strength here, which is basically calculated by the voltage potential difference between these two plates divided by the separation of the two plates. So the potential difference is actually 3000 volts. The separation is 5 millimeters. That's why you see 3000 divided by 5 millimeters. It gives you the electric field strength here. So when you compute and then you have substituting the values, so you basically have Q to be 1.6 times 10 to the negative 19 coulombs. So we can come over here, and then Roman B says another oil drop of mass that is held stationary when an electric field is applied between the two horizontal plates. If the drop carries 6 electric charges each of value that, calculate the value of the electric field strength. Okay, so if it's held stationary, it means that the electric field, of course, equals to the weight, all right? Because the only thing that is going to hold this man stationary is if you reverse these plates. Now, these two plates now become horizontal plates. You can see clearly here they are talking about what? Applied between the two horizontal plates, all right? So we're now saying that, all right, so that it means that the weight now is going to be balanced by the electric force. So that's why you see eq equals mg, and then you can basically calculate E here. So our mg, of course, the mass, which is 4 times 10 to the negative 15 kilograms, multiplied by g, which is 9.8, divided by q. And the q here, if it has 6 electric charges, right, you notice that you see 6 electric charges. So each of value 1.6 times 10 to the negative 19. So we basically have 6 multiplied by this to give you the total charge, which gives you 9.6. 9.6 times 10 to the negative 19. So you get that ratio, and then our E is basically 41 kilonewton per coulomb. All right. So we can just go ahead and then say that C. All right, you notice I have not used negative here, right? So this negative here is not reflected in the answer here. Well, that's because electric field strength is a vector, and well, it's actually negative, basically depending on the electric charge. So it's basically direction, really. It's basically direction. So it's positive pointing in a certain direction and negative pointing in the other direction, depending on the charge that is placed in the electric field. All right, so that's why I've just ignored the negative there. All right, so C says that in the ionosphere, electrons execute these revolutions in 1 second. Find the strength of the magnetic flux density B in the region. So they've given you the specific charge is 1.8 times 10 to the negative times 10 to the 11 coulomb per kilogram. All right, so to get the strength of the magnetic flux, we have to of course use the centripetal equation. So what provides the centripetal force in the ionosphere is basically the magnetic force, P Q V equals m omega squared r. So but our V here is omega r, remember that, so we can cancel out all these omegas and r's, and then we basically have B magnetic field strength to be equals to m omega over q. But remember that we have the specific charge already, okay? So we can actually have q over m. So we just take this m here, send it down here, so you have q over m, omega over q over m. This q over m already is 1.8, so we basically have our omega to be 2 pi multiplied by this. All right, so we actually have 2 pi f over this. So our B is substituting those values, we actually have 4.9 times 10 to the negative 5 Tesla. By the way, people think that Nikola Tesla was one of the most underrated scientists. The magnetic flux density is actually the unit of the magnetic flux density is actually named after him. Like, I mean, science has a way of crediting these guys, and it's always a pleasure, having to solve things. High school students and university students solving things, you know, and just basically having the units of those things after maybe somebody, right? I mean, that goes on for ages, and it's such an honor. I want to get my name there someday. All right. Okay, so our question 6 is a question on simple harmonic motion, and the students had to answer both the question 6. So in the GC you have either or, but here we ask them to answer both. So for a body undergoing simple harmonic motion, the displacement s and velocity at time t can be related by certain equations. Write down an expression for the maximum speed of oscillator in terms of f, the frequency of oscillation, and a, the amplitude. All right, so we actually have this system, so we are going to just solve it here. So to get that velocity they're talking about here is basically omega a, right? So but our omega, remember, that is 2 pi f, so we actually have that v to be equal to 2 pi f a. So velocity of system, that's the maximum velocity. Remember that we're asking for the maximum speed, so it's omega a and it's 2 pi f a. All right, so a is the amplitude, f is the frequency of oscillation, and then v is the maximum speed. All right, so we can go on. Roman 1 says that calculate the frequency of oscillation of the system. So if this is a period, so the frequency is just going to be the reciprocal of this. So it means that we have reciprocate everything here. So we're going to have 1 over 2 pi. Then if we reciprocate L over G, we're going to have G over L instead. So put in the values. So of course 2 pi is not a problem. So G is 9.8, L is basically 15 here. Put that in, you have frequency to be 0.13 hertz. So Roman 2 says that the suspension cable is vertical when the sphere hits the wall. Calculate the speed of the sphere when it hits the wall. So if the suspension cable becomes vertical when this guy hits the wall, it means that the wall is just aligns with the equilibrium position of this system. So we are going to have the maximum possible speed at this particular point, right? So that maximum possible speed is basically 2 pi fa, remember from above. So our f is this, our a, amplitude of oscillation, is basically these three, right? So this is maximum possible displacement. Then boom, it swings back to this equilibrium position, and it has to cover this distance. So that's why we're calling that our amplitude. And then that gives us 2.45 meters per second. So Roman 3 says that determine the kinetic energy of the sphere when it hits the wall. Alright, I've already done that. So kinetic energy when it hits the wall basically is going to be half mv squared, and v here is basically the maximum velocity, right? Because it's basically the wall aligns with the equilibrium position, and around the equilibrium position the velocity is maximum, and the velocity is basically 2.45. So we're going to put that in. The mass of the bulb is basically 2,500 kilograms, right? This is it over here. So we plug that in, we have kinetic energy to be 7.5 times 10 to the power 3 joules. And then we come over here, Roman 4 says that state with reasons whether using double the mass or double the initial displacement will provide the greater increase in kinetic energy. Alright, so in physics when they say state with reasons like that, you don't write grammar, just go and show it. Alright, So doubling the mass, we are going to have the new kinetic energy to be half. Doubled mass is 2mv squared, so we actually have mv squared. This is our new kinetic energy. Instead of half mv squared, we now have mv squared. It means that the kinetic energy has doubled, right? So if you double the mass, the kinetic energy doubles. Notice that kinetic energy, of course, kinetic energy is directly proportional to mass. Can you see that? This is Ke here. So this is our Ke is directly proportional to this mass here. So if you double this mass, you're going to be doubling this kinetic energy. Perfect. So that's why this guy has basically doubled here. Now, but if you double A, which is the amplitude of oscillation, so if you double this guy from 3 meters to instead 6 meters, what is going to happen to the kinetic energy? Let's find out. So if you double this guy, you notice that the velocity here will also double. Do you notice that the velocity here will also double? And the max, if that maximum kinetic energy velocity doubles, it means that kinetic energy does what? So you are going to come here, half m, in place of velocity, you are going to have 2v squared because it has doubled. Now the new kinetic energy is 2mv squared. It has quadrupled. Of course, you expect that to quadruple because, again, look at this. Kinetic energy is proportional to the square velocity. It means that as velocity doubles, kinetic energy rather quadruples. Okay, perfect, good. So again, the examiner says state with reasons whether using double mass or double initial displacement will provide a greater increase in kinetic energy. So this is already a reason because the calculations is your reason. You don't have to write grammar here. So doubling the kinetic, the displacement will quadruple the kinetic energy, and it gives it the greater kinetic energy when it strikes the wall. Perfect. So we go on. The last part is calculate the angle. So we're not going to solve the last part here. We're going to do it in the next slide. So let's just go to the next slide. All right, so the next part is calculate the angle the string makes with the downward vertical running along the face of the wall and the height the ball falls through when it moves from the position indicated on the diagram to when it hits the wall. Okay, so again, this is our diagram here. So again, we can basically calculate the angle we're talking about. The vertical is basically, all right, I've not just drawn this thing very well. So if you come vertically downwards like this, let me just use pen there. So if we move from here and then come vertically downwards like this, oh no, that's not straight. I mean like this. I'm trying to make it straight, but you get the point. So there's an angle here that I'm asking for. This is the angle. So this wall is supposed to be here like that. So what is this angle? All right, perfect. So we're going to get that angle by basically saying, all right, sine theta, because again, remember that this is basically opposite over this hypotenuse here. Now our hypotenuse is 15 meters and our opposite is 3 meters. So we're going to get our theta to be sine inverse of that, which is 12 degrees. And then to get this height, right, the height that this guy has to fall through now all the way to get to this point when he hits this wall. All right, so to get that height, we're basically going to get the total length here, because when it's hitting the wall, this guy is vertical, so the total length, which is 15 minus L cos theta, and our L cos theta now, like that will be this 15 cos 12. All right, so we actually have this, and then it gives us 330 millimeters. All right, so again, that's basic, and then our mark allocation is basically that 1 mark. All right, on to the next part of the problem. So this is about this question indicated here. You can just pause the video again and then just read the question and attempt it by yourself before I start solving across here. So I'm going to start solving here. So this says that why is there a change in gradient of the slope of the graph? Sorry. So we actually have the graph like that, and then there's a change in slope. So why? So of course this is due to the spring's compressional limit being exceeded, because remember that you're holding this toy and then you're pressing it down and then you're compressing this spring. All right, so the compression, the force is plotted against the compression like this. Okay, so you will notice that you're going to compress it as you keep increasing the force that's compressing this spring. You're going to get to a force where, I mean, you're increasing, the thing is no longer compressing, right? Because of course the compressional limit is exceeded, so you cannot compress further. All right, so the next part of the question says the spring is compressed by punching the head down 20 millimeters. Use the graph to calculate the energy stored by the spring when it has been compressed by 20 millimeters. So energy stored by the spring, this is our 20 millimeters here. So we're just going to come here, and then energy stored by this spring is basically going to be the area under this graph from the point origin all the way to this 20 millimeters. So what is this area? Of course, it's just this triangle. So we actually have half base times height, gives us that, and So it's basically this triangle like this from here. Oh no, I've not drawn it well. Again, you get the point. So this is half base times height, and that is it over here. So it gives us 0.04 joules. And the next part, Roman 3 says, estimate the maximum distance through which the toy will eventually rise. The toy mass, this is then released. Okay, so the maximum height through which the toy eventually rise, is that Roman? Oh no, I've skipped Roman 2. What has happened to this energy at the time the spring has just returned to its uncompressed length? Alright, so what has happened to that energy? All of the energy has been converted to what? The kinetic energy of the toy. Alright? Yes. So all of that energy is converted to the kinetic energy of the toy. That's provided we are neglecting frictional forces and air resistance. All right, so that, because part of that energy will of course be overcome that, but again we are ignoring that. So all of the elastic potential energy that we have calculated here is converted to this toy's kinetic energy just when it reaches, just when the bob or the spring gets back to its original length. All right, so Roman 3 now says estimate the maximum distance through which the toy will eventually rise. Okay, so the maximum distance through which the toy will eventually rise would actually have mgh. All right, so because at the maximum height, mgh is the amount of work the toy has done against gravity, and that is basically aided or is at the expense of what? The entire initial spring potential energy. And this is the spring potential energy, so that basically gives us mgh equals to that energy, and of course our h is basically that, and we can notice that the h is basically 14 centimeters there. The next part says that in practice the toy does not rise as far, so just one reason for this, of course, work done against resistance. So good. So the next part says that a student suggests that when the spring is compressed by 10 millimeters, the toy will only reach half the estimated maximum height. So you are halving this compression, right? The student is suggesting that the toy also reach just half of this height. Without detailed calculations, comment on this suggestion. Of course, it's wrong. How do you know that? Of course, all right, we're going to say Ke is half mv squared. So in place of Ke, we're going to have half m omega squared a squared, right? Because v here is maximum velocity. So maximum velocity is of course omega a. So we square that, it gives us that. Now, all of this energy is actually used up to get to this particular height h. All right. Now, remember that this is a here. This is a squared, which is basically the amplitude. This is the energy that is used up to get to that particular height h. Now, for the new kinetic energy, you have actually halved that amplitude. The original amplitude was just a, which is 20 millimeters in our case, but now you're halving that amplitude. So the kinetic energy of the particle will now go to what? Will now go to a quarter of this original kinetic energy. And remember that this is just proportional to how much the height the guy reaches. So the height the guy reaches now, this time it will not be halved, but it will be a quarter of the original height. All right, so the student was actually wrong, but you know that without detailed calculations. Again, you just see what I've done, and that's what you're supposed to do. So again, the mark allocation here was just like that. Thank you guys so much for watching. This was how our KC exam looked like this time around. And of course they also had data analysis, but of course I could not put that up on the channel. Hopefully we're going to create that time to do a data analysis video, and hope you guys stick around to enjoy. If you enjoyed this video, please like, comment, subscribe, and share it to your friends. Thank you guys so much. Keep being curious as always. We love you from Casey, and for the love of science, till we die, keep looking up and stay curious. All right, thank you guys so much.